The field of view of a microscope is a concept that's pretty easy to understand if you have the microscope in front of you, but it can be quite tricky if you don't have a microscope like with the labs that you're doing in this course. So I want to go through just a couple concepts and kind of help you with this part of the lab because it can be difficult to understand without having a microscope to look through. The field of view is just a term, a vocabulary term, that refers to what you can see with your eyes as you look through the eyepiece of a microscope. So it's that portion of the microscope slide that you're able to focus on using the different objective lenses. So when you look through a microscope, if you have the eyepieces adjusted appropriately, you should see one circular field of view. And so when we're talking about the field of view diameter, we're either talking about the width here or the length. Either way is going to be the diameter since it's a circle. It's going to be dependent upon both the magnification of the eyepiece itself, which you'll recall from your lab is a 10 times magnification, or 10x, plus the magnification of the objective lens, which depending on which lens you use will be either 4x to 100x, which is the oil immersion lens. As you'll recall from your lab, whenever you're calculating the total magnification, the way that you do that is you multiply the magnification of the eyepiece times the magnification of the objective lens. So if you're using the 4 times objective lens, your total magnification would be 10 times 4, or 40. So as you're zooming in on the microscope, a higher power objective lens, so as you go from 4 to 10 to 40 to 100, as you get higher and higher, you're getting a stronger magnification, so you're zooming in. And because of that, you can see more detail at what you're looking at, but you're going to see less of the overall picture. And what that means is that the field of view is going to get smaller as your magnification gets higher or gets stronger. So this series of butterfly pictures is a good example of this. When you have just the regular butterfly that you're looking at, you can see the whole object. You have a wide field of view, but you can't see many details. So as you zoom in, you can see that the field of view, the part of the butterfly that you're seeing, is getting smaller and smaller. But what you can see is more and more detailed. You can see down to the little tiny particles on the wings at this 500x magnification. So that's kind of a key concept, is that as you're measuring the field of view, the size of that, the diameter or the width or the length, or however you want to use, what term you want to use, that's going to get smaller and smaller as you zoom in more and more. So as your objective power gets higher, your field of view is going to get smaller. And so you can use that knowledge to figure out how to measure things using the microscope. So in your lab, you have a picture very similar to this, where basically you're looking at a ruler through the microscope. So if you had a ruler and you use the lowest power objective, so we're using a 4x lens with a total magnification of 40x because of the eyepiece, 4 times 10 is 40. When looking through that and looking at the ruler, you can see these black marks on the ruler, and each of these black marks is 1 millimeter. So if we're measuring the width or the diameter of this field of view, we can say we've got 1, 2, 3, 4, and some change. So we basically got 4 millimeters, and we're going to say it's 4.4. That's the formula you're going to use for your lab. So the width, the entire width of this field of view is 4.4 millimeters. So what you're doing here, let's just draw a little line so you can see what I'm talking about. You're measuring. So you're starting at one end of the field of view, and you're going to be measuring. You're going to be measuring how far it goes down. So starting with the first time, you're going to go down to 1, 2, 3, 4. 4.4 millimeters is the width of that field of view. So knowing that knowledge, that you've got 4.4 millimeters for the width of view using the lowest magnification lens, the 4x lens, you can predict the width of view for the field of view for the other objective lenses. And so your lab manual gives you a formula to use to predict this. And here's the formula. The formula starts with, it's a fraction. On the top part of the fraction, you're multiplying the diameter of the scanning lens field of view in micrometers times the total magnification of the scanning lens. So let me back up just a moment just to remind you. Each millimeter is going to equal 1,000 micrometers. Because things that we look at under the microscope are so very, very small, we typically use micrometers to measure those objects. And so 1 millimeter equals 1,000 micrometers. It's just a metric unit of measure. So the width, if it's 4.4 millimeters, is going to be 4,400 micrometers, because 4.4 times 1,000 equals 4,400. So the width of this field of view is 4.4 millimeters, or 4,400 micrometers. So when we're looking at this calculation with this formula, you're going to use micrometers for your diameter, which we know to be 4,400 because we've just measured it using that ruler, times the total magnification of the scanning lens, because that's what we're using as our base of measure. And we know that that's going to be a total magnification of 40 because it's a 4x lens and you've got the 10x magnification on the eyepiece. So the number that goes here is going to be 40. And then what you put down here is the total magnification of whatever lens you're wanting to calculate. So if you're wanting to calculate the low power lens, you would do the total magnification for the low power lens. And so let's look at an example here. And when you do this calculation, your end result is the diameter of the field of view of your desired lens. So here's an example, low powered lens. We know from what we just measured that the diameter of the scanning lens field of view in micrometers is 4,400 micrometers. We know the total magnification of the scanning lens is 40x. So we're dividing by our desired lens. We want to know about the low power lens, which is the 10x lens. The total magnification of the 10x lens is the 10 times power from the lens multiplied by the 10 times power from the eyepiece, which gives us a total magnification of 100x. So according to the formula, you multiply 4,400 times 40 and you divide by 100. And what you get is 1,760 micrometers. Now we know, as we discussed, that 1,000 micrometers equals 1 millimeter. So 1,760 micrometers is equivalent to 1.76 millimeters. So as you zoom in, your field of view gets smaller. So it makes sense that if the field of view under the scanning lens is 4,400, that the field of view for the low power lens would be smaller. So 1,760 makes sense. That's a logical conclusion. Let's do one more example. Let's do the high power lens. So according to the formula, we start with what we know on top, which is that the diameter of the scanning lens field of view is 4,400 micrometers. The total magnification is 40. And then we want our total magnification of the desired lens. Well, our desired lens is the high power lens, which is the 40x lens. For the total magnification, you multiply the 40x lens times the 10 times magnification from the eyepiece. So that gives us a total magnification of 400. So according to this formula, you multiply 4,400 times 40 divided by 400 to give you 4,400 micrometers. Well, we know that 1,000 micrometers equals 1 millimeter. So 4,400 micrometers would equal 0.44 millimeters. So you can see it's a dramatic change. The field of view gets much, much smaller as you get more and more zoomed in, a higher powered objective. And knowing that information, you can then measure different objects or specimens that you're seeing through the microscope. So here's an example of that. Let's look at this first picture. If you're looking through the microscope and you're using the 10x lens, which is a 40x total magnification, you're looking at this object, this specimen. What you're going to do to estimate the size of this specimen is you've got to know the size of the overall field of view, which we just calculated by measuring this ruler, that it's 4,400. So if we know that the entire field of view, as indicated by this long arrow, is 4,400, what we care about, or what we're trying to measure or estimate, is the size of this little object. Well, you can say roughly that this arrow, the size of this object, which is indicated by this arrow, is about 1/3 the size of the total. So if we know that 4,400 is the total, and we're trying to estimate the size of the object, we would say the object takes up roughly 1/3 of the field of view. So we can estimate its size at 1/3 of 4,400, or you could say 4,400 divided by 3. So 1/3 of the overall field of view, and that gets us 1,467 micrometers. Obviously this is an estimate, but that's what your lab is wanting you to do, is kind of estimate the relative sizes of objects. Here's one more example. This is not one that's going to be in your lab manual, but this is just a neat example. This is an image of cocci bacteria. They are red because they've been Gram stained, which is a particular type of stain you use to differentiate different types of bacteria. But this is cocci bacteria. They're tiny, tiny little circular bacteria, and you can see them. They're clumped together. So like right here where I've got this little arrow, that's actually 4 of them that are clumped together. And this is zoomed in as much as you can do. This is the oil immersion lens. So it's the 100 times lens with 1,000 times total magnification. This is oil immersion. We know, or we can calculate, based off of this formula, that the oil immersion field of view, as indicated by this longer arrow, is only 176 micrometers. So that means these cocci bacteria are teensy, teensy tiny. You could estimate them to be roughly 0.5 to 1 micrometers, because it would probably take about 200 of them to fill this whole length. If they were lined up in a row, there are probably about 200 of them to take up the whole width of the field of view under this oil immersion lens. So that is why we use micrometers, because a lot of what we're looking at is very, very small. A typical cell, which is what these bacteria are, is around 1 micrometer, give or take. So we have to use small units of measure to do this, to measure these objects. And so that's why it's important, because obviously this object is much, much smaller than this object. But if you don't know the relative differences in the fields of view and kind of the widths of those fields of view, you might not know that. You might say, oh, well, yeah, this is a little bit bigger. No, it's enormously bigger, because this object is it's almost 1,500 micrometers. These are either a half to 1 micrometer. So that's why this is kind of important information to know from the microscopic point of view, is it helps you differentiate those things and kind of keep track of where you are. So hopefully this will help you as you work through the lab, give you some details. I will post this document online as well, so you can kind of read through it and look through it, and hopefully that will be helpful. If not, let me know.